Okay, yeah, recording is started. Matt, you are good to go.
All right. Hey, everyone. Thank you for coming today. I'm Matt, and I'll be giving my area exam presentation today on establishing shared mental models for improved human-robot team performance. So before we go into the technicals, I'll just give a little bit of background on myself. So I have a bachelor's in computer science I got from Cornell University in Ithaca, New York, an internal concentration in robotics and AI, and an external in psychology. After I graduated there in 2018, I moved to CU Boulder to start a PhD program. I've been TAing classes since 2015, which is my sophomore year of undergrad. Intro computer science classes, computer systems classes, AI classes for many semesters. And I've also been researching in robotics labs since 2016. So at Cornell, I worked in that building in the top right in the Robotic Personal Assistance Lab. And here at Colorado, I work in the CAIRO lab with Brad Hayes. I've also spent 5 summers interning at NASA's Jet Propulsion Lab in Pasadena, California, which is definitely one of the highlights of my career. I've done work in instrument data systems and rover planning systems, and I've worked on 3 Mars surface missions. So I've worked on the Perseverance rover for all 5 summers, which is in the news a lot recently. I worked on the InSight lander for 1 year, and I also worked on the surface ops team for Curiosity. So as part of that, I was able to participate in 2 days worth of rover driving, which is generating the actual commands for Curiosity as it drives from target to target on Mars. And through that, I was able to accrue a career Martian odometry of 65 meters, which is without a doubt the coolest thing I've ever had an opportunity to do. So that picture right there is the Perseverance rover team, and here's me. So let's start by taking a look at a few robots in use today in the real world, which means robots that are meaningfully and successfully deployed outside of a lab setting. So we have the Roomba from iRobot. So this is a very commercially successful bot. It'll help clean your home. We have robot arms, like in the bottom corner, we have a KUKA arm. These are widely adopted in manufacturing settings, especially the automotive industry. We have Amazon robots moving pallets around their distribution centers. We've got surgical robots like the Da Vinci to allow surgeons to make minute movements that would be hard to do by hand. And then, of course, we have a whole variety of space robots. Nearly every mission to space involves a robot. We have Perseverance and Ingenuity there, and we have the Canadarm2 on the International Space Station. And you'll notice that all of these robots either operate on their own, independent of human effort, or they're directly operated by humans. So this kind of leads to the 2 distinct paradigms that you tend to see for modern robots. So first of all, you have pre-programmed autonomy. This is the classic robotics loop, the sense, plan, act loop, where a robot acts to affect change in its environment and senses those changes within the environment and then uses that to replan. And on the other side of the spectrum, we have teleoperation, where now the robot is acting as a proxy for a human operator. Maybe it's doing a task that a human couldn't, like lifting a heavy object, or it's operating in an environment that a human couldn't get to, like outer space. So in this case, the human passes on actions as commands to the robot, who then executes them in the environment and passes its sensor readings back to the human to allow them to plan. So we know that humans and computers excel at different things, and we've known this for a long time. This list on the right is from 1951, although some of these attributes are a little out of date now that computers have advanced so much. So as an example, after Deep Blue beat Kasparov in chess in 1996, chess centaur games were very popular, which is combining a human player with a chess engine that suggests moves. And these centaurs were able to soundly defeat even the best chess engines all the way until very recently, with the deep learning revolution in chess, where the value of the human has started to diminish. So chess is a very structured domain with very well-defined states and actions. So it's the perfect domain for an AI. But most tasks in the real world are not so well-defined or perfectly suited to AI. And so humans could easily provide benefit to autonomous systems in those domains at least until the AI becomes good enough to fully outperform a human AI team, which appears to be decades from now for many tasks. So for example, you could imagine a Centaur-style Mars rover architecture, where a rover is capable of driving on the surface and avoiding obstacles all on its own, while still having operators on the ground reviewing data and telling it which activities would be most valuable to pursue. So that would leverage both human scientific intuition combined with robust autonomous control. And the challenge is really leveraging these differing skill sets properly as a combination, which is rarely a trivial problem. So since we want humans and robots to work together, we can introduce some new paradigms where human and robot agents are treated as teammates. So first, we see a scenario which looks on the surface a lot like teleoperation, but now the robot has its own planning capabilities. So we can call that remote collaboration. And the human provides commands, perhaps they're at a high level or perhaps they're suggestions. And the robot then takes those into account as part of its own planner. And the robot is able to act and sense and pass on information just as normal. And we can also have shared environment collaboration now, proximal collaboration, where a robot and a human are sharing the same space, each running their own separate sense plan act loops. And so if you look at modern factory floors, humans and robots often work in totally isolated spaces on independent tasks, but this tends to severely limit their collaborative potential. So you'll notice that these look a lot like human team architectures, but if we want to exhibit teamwork and not just individual effort, we're missing a degree of planned synchronization. So how can we synchronize? We can use something called a mental model. So mental models are organized knowledge structures that allow us to interact meaningfully with our environment. They're basically mental shortcuts that we hold in our minds that represent how processes work in the real world. And we gain them largely from experience. So human factors research has shown that as similarity increases between mental models of human teammates, team performance increases accordingly. So humans are pretty good at synchronizing mental models when working on a team by communicating with their teammates or observing what their teammates are doing. But robots don't get any of that for free. So they need to rely on specific mathematical formalisms to mimic that communication and observation. So we need to transform between human planning spaces, which are subjective and they differ from person to person, and robot planning spaces, which tend to be centered at its core around some form of mathematical optimization. So we'll now get into a brief literature review on this topic. So myself and Ankib wrote a survey paper last year on mental modeling techniques in human-robot teaming for the journal Current Robotics Reports. Although not every paper I'll talk about in the presentation today is included in this paper, it's definitely a good thing to check out if you're interested in learning more about some of the topics I covered. So we'll start by modeling humans as teammates. So that's all about getting the robot on the same page as their human collaborators. And we'll then talk about the opposite problem, getting the human on the same page as the robot through communication. And that communication can come in a few different flavors, like visual, natural language, or behavioral, all of which I'll talk about. I will touch on some desiderata and evaluation techniques that are used in this field. And then lastly, I will talk about a specific paper in technical detail. So we'll start by talking about a few methods of modeling humans and shared tasks with robots. So the most natural and obvious assumption is, why don't we just treat humans as rational beings, like the famous principle of rationality states from economics. So in this case, we would want to establish some kind of reward or objective function that humans should maximize, and set loose a rational planner to predict what the human would do, essentially treating it as a robot would. So we could use maybe an MDP or a Markov decision process. Those are super common ways to represent environments with rewards to plan through. And I'll discuss MDPs in greater detail later in the technical paper. Of course, we could assume that humans are perfectly rational, but that doesn't tend to describe real humans. So humans have been known to act suboptimally for one reason or another. So one technique is simply add a bit of fuzziness to represent the human in predictability. So if we fit a Boltzmann distribution around an ideal action, we can achieve this. This is called Boltzmann rationality or noisy rationality. One issue with this, though, is that it assumes that the optimal action is the most likely action always, which is actually frequently not the case with humans. So Quant et al. Built off this in a recent paper, which leverages Kahneman and Tversky's Nobel Prize-winning work called Cumulative Prospect Theory, which describes how humans can be predictably irrational about overvaluing potential negative rewards compared to potential positive rewards in order to model human behavior more accurately with a risk-aware model. Now, we don't necessarily need to spend all this effort guessing how humans would behave if we can observe them doing the task and learn how they would act from that. So this is the key insight behind inverse reinforcement learning, or IRL, which in modern literature is used quasi-synonymously with a bunch of different terms and techniques like apprenticeship learning, or imitation learning, or learning from demonstration. So if you look below to the figure, in standard reinforcement learning, you give an agent an environment to explore with reward signals, and it converges on a behavior. But those reward signals are often always guesses of some sort. So the real world doesn't come annotated with rewards. So these signals are often imprecise by nature. Now, inverse reinforcement learning is predictably the inverse process, where you instead observe the behavior of a human expert operating within your environment, and then converge on what you think the human's implicit rewards might be, such that their behavior appears optimal. And then you can use those rewards that you model to model the human as a standard RL agent in a shared task. So one popular algorithm for setting these reward values is maximum entropy IRL from Zebart et al. So first, maxent IRL assigns a probability of observation to every possible trajectory that a human expert could take within the environment, while assuming that higher reward trajectories are exponentially more likely to have been observed than low reward trajectories. And next, they find the reward parameters that maximize those observation probabilities from the expert's actual trajectories. And that's how they define their reward function. So we can extend this with cooperative inverse reinforcement learning. So there are a few problems that tend to crop up with expert demonstrations. So first of all, there's the issue of correspondence. So human and robot policies might not be perfectly aligned. So if a robot is learning to make coffee and they're able to observe their human perfectly, they would also learn the human's desire to have a coffee rather than just desiring the human to have one when it wants one. Second, expert demos rarely visit unplanned states. So a robot might have no idea how to get out of those. So imagine training a system to race a Formula One car by watching Lewis Hamilton. So what should the system do if it fails and runs off the track on the first turn when it's never seen Lewis Hamilton ever get into that scenario? So we want the robot to have an active role in shaping this. So this paper models interaction as a cooperative game where the human and robot share the same reward function, but that this reward is unknown to the robot. So this encourages value alignment as the robot is attempting to learn and maximize the human agent's reward rather than just learning it to copy it. So this could also help prevent adverse scenarios like the futuristic stop button problem in AI, where a robot ignores you trying to shut it off in order to keep maximizing its reward. Since in this case, it would recognize that the human reward is what it's trying to understand and maximize, and that shutting off the robot would probably provide positive reward to the human if they're attempting to do it. So next, we'll move on to the opposite direction of information flow in communicating robot state and plan information to their human teammates. So first off, I'll discuss a few emerging techniques for visual information communication, starting with augmented reality, which is a technology that I personally am very excited about. So AR devices have been steadily improving over the past decade, and they provide an incredible way to visualize robot states and robot motion plans to humans in situ, in the actual environment, which provides a much better situational context as compared with monitor-based displays. So AR has been shown to improve human ability to anticipate robot actions with multiple types of robots, such as projecting holograms of a manufacturing arm forward through space to represent its trajectory, as Rosen et al. Explore, or a number of different interfaces that Walker et al. Explore for conveying aerial robot motion, like environmental waypoints or flight path arrows or gaze overlays. So another merging technique, which I think possesses good potential for human-robot interaction, are visual counterfactuals, which identify spatial regions of images that, when swapped with spatial regions from another image, cause a machine learning classification of that image to change. So for example, if we swap the beak of a crested auklet with that of a red-faced cormorant, this would change the classification. So this could be helpful for alerting humans of salient features in a robot's environment representation, say an environment map, that would cause a change of the robot's plan, which allows the human to gain a better understanding of the robot's potentially opaque reasoning process. Now we'll move on to semantic or natural language explanations. So as previously mentioned, a barrier to human understanding of robot actions is the uninterpretability of their planners. So this is doubly true for modern learning-based planners. So if we could answer questions about these planners in natural language form, this would greatly help the humans in understanding their robot teammates. So Hayes and Shaw introduce a set cover approach for generating and combining into natural language a minimal list of predicates that satisfies a human's query. And this allows the human to receive an answer that requires no internal knowledge of the planner underlying the robot's actions. So much like visual counterfactuals, we can leverage the ability to generate these predicate-based explanations to do the same process with language. So as a side note, if you're wondering what the obsession with birds is in counterfactual papers that have separate authors, both papers use the Caltech UCSD birds dataset, which is a visual identification task that even humans have trouble with. So these contrastive explanations, like I did action A instead of action B because condition C was true rather than condition D, give more information and context about the internal reasoning of these robots to human collaborators compared to just a list of true predicates. We can also use natural language explanations to fix a human's incorrect assumptions in situations where the human has more expertise in a domain than their partner human does. Whether this involves repairing flawed notions of reward when a robot observes a human performing a suboptimal action, as Tedrez et al. Explore, or by initiating explanations to reconcile models when a robot's action would seem suboptimal from the human model's perspective, but is in fact optimal from the robot's perspective, as in Chakraborty et al. So now we'll move on to the last form of human-robot communication that I'll talk about, which is subtler and more implicit, and that's the behavior of the robot. So take, for example, this paper from Dragan et al., which develops and compares two robot controllers. One is predictable, which means its path planning minimizes surprise and maximizes the safety and efficiency of motion, and seems the most sensible if you know the robot's goal in advance. The other is legible, meaning its path planning focuses on being easily understood by humans watching it, allowing them to identify the goal from observing the path itself. So take a look at the figure on the right. The gray robot with the predictable controller takes a straight line path to the green ball, but you can't quite tell which ball it's aiming for until the very end, which is represented by those likelihood bars to the right of the arm. On the other hand, the orange robot takes a legible path, so it sacrifices efficiency and arcs out to indicate that it's aiming for the green ball very early on rather than the red. So these properties of predictability and legibility are often conflated, but this paper demonstrates that they're actually different and they're actually diametrically opposed behaviors in some scenarios. So we can also use robot behavior to correct the often flawed assumptions that humans make about what a robot is capable of. So Nicolaitis et al. Use a game theoretic model to weigh the value of a robot taking actions that reveal its capabilities or lack thereof to a human, thus improving that human's understanding of the robot of a collaborator, versus taking actions that are simply optimal with respect to the information that the human has. And they find that this improves performance over simply assuming that the human has an accurate knowledge of what the robot is capable of. Similarly, Quan et al. Introduce a method for generating motions that attempt to express both what a robot is trying to achieve and why it can't achieve it. So in this example, this robot is lifting its elbow to indicate that it wants to lift its cup, but it's unable to provide the torques necessary to do so. So before I go deep into the technicals of a individual paper, I'd like to take a quick step back and summarize what we're trying to achieve through these techniques for synchronizing mental models. So we want to achieve interactions that are fluent, adaptable, and trustworthy. And we also want humans to have a deeper understanding of both what a robot is likely to do next, as well as the robot's reasoning behind its own actions. So to measure whether our attempts at achieving these desiderata are successful, we have a number of evaluation metrics that can be used in these papers. So first and most obviously is objective task performance. So why would we bother trying all this stuff with mental models if it doesn't improve performance in some way? Next are behavioral measures. So this refers to observing how the human behaves in presence of the robot. So there are plenty of these measures to see how trusting a human is of a robot or how fluent their collaboration is. And then lastly, there are a number of validated subjective measures, and these are usually given in survey form. So we have self-reported robot understanding, human task load, human trust in the robot, etc. So now I'll present the following paper in detail. It is Human-Robot Cross-Training, Computational Formulation, Modeling, and Evaluation of a Human Team Training Strategy. And this is by Stefanos Nikolaidis and Julie Shaw from the HRI 2013 conference. So I chose to talk about this paper, firstly because it's topical. It introduces a novel and interesting way of establishing shared mental models between human and robot teammates. And I also wanted a chance to talk about some of the common technical formalisms that are used in shared mental modeling research. And this paper utilizes both Markov decision processes and interactive reinforcement learning, which appear in many papers in this field. So the big idea of this paper is based on a technique from human teamwork research called cross-training. And this is where humans rotate their tasks during training. So for example, if human A is assigned to task A and human B is assigned to task B in a scenario that involves teamwork, cross-training would involve A performing task B and B performing task A to allow both teammates to get a better sense of their counterparts' responsibilities and all the points of interaction. So the authors apply this model of training to a human-robot team where the human and robot switch tasks. And this is all in an attempt to get at that specific human's shared task model, as it differs from a pre-trained shared task model, which is gotten from other humans. So they found that this technique, cross-training, improves convergence to the human's mental model. It also improves perceived trust and competency of the robot, as well as objective team fluency metrics when compared with existing reinforcement learning techniques. So first of all, we need to model our interrole knowledge. So this is the formulation of the shared task that the human and robot will share. So to do this, the authors utilize a Markov decision process, or an MDP, which is just a way of specifying an environment in a task. So MDPs are simply defined as a four-tuple S, A, T, and R. So for this paper, we have S, the set of all world states in the environment. We have A, the set of actions that the robot can execute. And notice that this is only robot actions modeled in A, not the human actions. Those are instead modeled through T. So T is the state transition function. It takes a state and an action pair, and it outputs a probability distribution over states that you would arrive at. So this models the uncertainty of human action, since these transitions are stochastic. So T S A S prime is the probability of going from state S to state S prime given action A. And R, which takes a state and an action and gives back a real number, is the reward function. So this is what we want to maximize. So RSA is the expected immediate reward given action A in state S. So in this paper's formulation, S and A will always remain constant, but we want T and R, the transition and reward functions, to change to suit the individual human collaborator. So these begin as approximations, which will get refined throughout the algorithm. And if we assign an action to every state, we get what's called a policy, which we denote with pi. And pi star represents the optimal policy, which would maximize reward throughout the entire episode. And this is what we want to approximate. So now that we have our environment and our task representation, how do we actually generate pi? So there are classical dynamic programming-based solvers like policy iteration or value iteration, which can solve MDPs, though they rely on the MDP being fully correct from the start, and they don't scale well. So reinforcement learning will serve as a good approximation of our optimal policy. So the authors use a specific reinforcement learning algorithm called Sarsa Lambda with a greedy policy. Sarsa Lambda keeps track of two things. The first is a Q function. So QSA represents the estimated value of taking action A when in state S. So this Q function is initialized arbitrarily for every state action pair, and it changes over time as the RL agent explores its environment. So if you greedily maximize the Q function looking one action ahead, you have your policy. So as the Q function evolves, this policy is actually guaranteed to converge on the optimal policy for the MDP, so long as it can visit every state and every action an infinite number of times. So if we just have the Q function, we can define what's known as Sarsa with no lambda. So if you look in the top right corner in the blue text, I've compressed Sarsa's update step into a one-liner for ease of understanding and explanation. So here, we set as the new Q function at state S and action A, the old QSA, plus a big sum all multiplied by alpha. This is the learning rate, which is set between 0 and 1, which sets how quickly Q changes. It's essentially a step size parameter. So this big sum is R, which is the reward observed from doing action A in state S, plus gamma, the discount rate between 0 and 1, which prevents this whole expression from becoming an infinite sum, times the Q function at S prime A prime. So S prime is the state you just arrived at from doing action A in state S, and A prime is the optimal action according to your greedy planner. So this is where the word Sarsa comes from. So it stands for state action, reward, state action, since those are all the inputs to this Q function update step. And then you subtract the old QSA. So if we want to make Sarsa into Sarsa Lambda, we need to add one more feature, which is called an eligibility trace, which is represented by ESA. And this is weighted by the lambda. So this keeps track of the states and actions that you've already seen. And it provides a form of memory to the RL agent that allows states further away from its current state to inform the Q function. So if lambda were 0, you'd have vanilla Sarsa, which looks ahead by exactly one step. And if lambda were set to 1, it would look all the way to the terminal state and sum all the rewards, which is equivalent to the Monte Carlo method. So keeping lambda between 0 and 1 allows the algorithm to look beyond the immediate neighborhood of states while still being an online method and not requiring travel to the end of the episode before recovering rewards. So if you look to the algorithm on the right from Sutton and Bardo, we'll quickly step through it. So we start by initializing the Q function to some arbitrary value for all state action pairs, and we begin our episode. So we initialize the eligibility trace to 0 for all state action pairs, and we pick a state S and an action A to start from. So for each step, we take action A and observe the reward we receive and the new state S prime that we land in. We then choose A prime from S prime using our greedy policy. The next line is simply a shorthand of the one-liner step I described. So if you look up to the blue text again and look inside the square brackets, that expression is equal to the expression on the right here on this line. And they're just setting that all to a shorthand of delta. So next, we increment our eligibility trace by 1 at SA. And this indicates that we've seen that action in that state. And so for all state action pairs, we update the Q function exactly the same as we would in Sarsa, but with the addition of the eligibility trace. So it's the old QSA plus alpha times delta times ESA. And we also update that eligibility trace everywhere by multiplying it by the discount rate and by lambda, which lessens the weight of ESA for every next step. And we continue stepping until we reach an end state, and we continue for as many episodes as we want. So now that we have our shared task representation and we have our means of generating a policy, let's step through the primary contribution of this work, which is the cross-training algorithm. So we start by initializing the transition and the reward functions from a generalized human model, which we now want to converge toward the model of our specific human collaborator. So we calculate our initial policy using Sarsa Lambda, and we enter a loop that runs what are called the forward and rotation phases of cross-training as many times as we want. So in the forward phase, we go from start to finish with the robot and the human doing their assigned tasks. We execute robot actions in the forward phase by just according to its policy, pi, and we observe the human actions and what state that would put you in. So from this, we can generate a trajectory or a sequence of states and actions. So S1, A1, S2, A2, et cetera, until we reach the final state. So from this sequence that we get, we can now perform a Bayesian update of the transition probabilities based on the transitions we've actually seen in practice. Next, we call the rotation phase, where we go from start to finish again, but with the roles reversed. So now, instead of taking action A as the robot's planner would dictate, we simply set A to whatever we observe the human doing. And we sample the robot action now from the transition probability to get the new state. So here we get the sequence of states again, same as before, until we reach the final state. And we use this to update our reward function. And specifically, the authors update this reward function by adding a constant value, small r, to the old reward function whenever the human performs action A in state S. And this indicates that this type of action in this state is preferred by the human in some way. And lastly, we generate our new policy given our new reward and transition functions. So to evaluate this algorithm, the authors set up a collaborative drilling task where the human places screws and the robot drills them. So though this task is fairly simple, it has a variety of strategies that the human could prefer, which range from the ordering of their placement of the screws to when they prefer the robot to drill a screw after it's been placed. So they start with a simulator-based training phase with 2 experimental groups. So we have group A, which is the human-robot cross-training method. And then we have group B, which just does the forward phase of training, but it includes a degree of interactivity where a human can give feedback for robot actions with a good, neutral, or a bad reward. So this is a standard method for adding some interaction to RL to accommodate human preference. So the R and the negative R in the brackets is the same constant, small r, as seen in the slide before. So after they complete their training phase, they move on to a real robot and perform the task with their original roles to get their evaluation metrics. So to measure success, the authors looked at mental model similarity and convergence. So for similarity, they used an existing technique in mental model literature, where before the evaluation phase, they had the human participants annotate an ideal sequence of actions for themselves and the robot. And then they take the ratio of the number of actions that overlap with the robot's policy to the total number of actions performed by the robot. For mental model convergence, they measured the entropy rate of the Markov chain as induced by policy pi on their MVP. So I won't get into the math behind that here, but this basically finds the cumulative uncertainty over the human actions as found in the transition function. So the idea is that as uncertainty over human actions decreases, mental model convergence increases. The authors also used a variety of objective fluency metrics like concurrent motion time, human idle time, robot idle time, and human-robot distance. And lastly, they asked a number of questions in a post-experiment survey to get subjective results. So what were their findings? So for mental model similarity, group A, which is the cross-training group, had 96% of human annotated ideal robot actions overlap with the robot's actual actions, as compared with 75% for the interactive RL group. For convergence, as you can see in this graph, the entropy rate drops faster with group A, indicating that cross-training leads to less uncertainty about the human's actions after 3 rounds of that training. So for the objective fluency metrics, Group A had a 71% increase in concurrent motion time. It had 70% the human idle time and 50% the robot idle time, indicating a higher degree of fluency. They also found that the human stayed closer to the robot on average, which would indicate higher fluency, though for some reason they did not give any quantitative data about that in the paper. They just gave a p-value. So on the right, you'll see the subjective measures for which A performed better than Group B with a high statistical significance. So we have in this round, Abby, which is the name of the robot. It's a play on the fact that it's an ABB robot. Performed her role exactly according to my preference, drilling the screws at the right time and in the right sequence. This is for the final training round. Then we have in the actual task execution, Abby performed her role exactly according to my preference, drilling the screws at the right time in the right sequence. I trusted Abby to do the right thing at the right time. Abby is trustworthy. Abby does not understand how I'm trying to execute the task. Note that this is a negative statement, and so the fact that Group A has a lower score is a good sign. And then lastly, Abby perceives accurately what my preferences are. So where does this sit within the mental model literature? So the authors combined with this clever cross-training strategy, the intuition behind interactive RL methods like clicker training, by having a human exercise some reward-shaping supervision over the learning process of a robot to speed it up, with the intuition of learning reward functions from directly observing human behavior. So when it's compared with existing methods in this space, they found that this allowed for better mental model synchronization in a teamwork context where the human and robots are contributing different actions to a shared goal. So of course, no paper is perfect, and there are a number of opportunities to improve on this great concept. So first of all, it was disappointing to see no objective task measures or performance measures included in this paper. So they referred to the place and drill domain as a proof of concept, but the task as a whole was basically impossible to fail due to its extreme simplicity. So not only would a more complex task that allows for failure allow objective task performance comparisons to be made, but it would also test the performance of the algorithm in a larger state space, which is where a huge quantity of papers in this field tend to fall flat due to computational complexity issues. So next, this paper makes a good deal of assumptions throughout, which simplify computability but decrease the realism. So first of all, the human is treated as having a singular preference for how the robot should behave. So though this may hold true for like this simple experimental task, real humans are much more unpredictable, and they may have their preferences evolve over time, which isn't captured. Second, the method of updating the reward function by adding a constant value small r whenever the human is observed taking an action is rather naive and could lead to overfitting whatever value is arbitrarily selected for that small r. And what's more, this method seems to rely on the human taking optimal actions on behalf of the robot, even though this is treated as a training phase where if the task were any more complex, you'd expect a human to make some mistakes that the autonomous system shouldn't necessarily be trying to learn from. So I'll wrap up my talk today by briefly sharing some single slides describing a few of my own projects as they relate to the synchronization of mental models. So we'll start with ArcLFD. This is a project which involves communicating a robot's conception of a task and its constraints as learned from learning from demonstration by using an augmented reality interface and allowing the human to edit and create new constraints within that same AR interface, allowing for mental model synchronization. Next, I'll talk about informed control handover, which involves communicating dangerous states with natural language to a human as they're tasked with taking control of a semi-autonomous system like a self-driving car in order to improve that human's situational awareness and performance post-takeover. And lastly, I'll talk about Avalanche Rescue with aerial drone teammates, which focuses on methods for communicating task uncertainty via spatial map to a human searcher, such that they have their search space coordinated with those of the robots. So ArcLFD, which stands for Augmented Reality for Constrained Learning from Demonstration, in collaboration with Connor Brooks and Carl Mueller, is an AR interface that extends Carl's prior work on improving learning from demonstration methods by including high-level constraints to encode information that isn't obvious from human expert demonstrations. So in order to make LFD more resilient to changing task requirements and environments, we introduced this AR system that allows humans to observe the robot's current conception of a desired skill by visualizing its trajectory in situ to see whether or not that trajectory is likely to succeed, as well as observe, edit, and rapidly create new constraints to add to the robot that it must adhere to with no programming knowledge required. So you can see the visualization of the robot trajectory along with a cylinder-shaped over-under constraint in the top image. So the ArcLFD system is successful in adapting skills to changing environment or task requirements without requiring any further demonstrations from the human. So this work is set to be presented at ICRA 2021 this June, and we also aim to extend the system for future work as well. So the Informed Control Handover project, which is along with Akib Tabrez and Karthik Siddharamana, focuses on the process of handing over control of a system in an emergency from an autonomous agent to a human. So since we can't count on the human to be paying attention to the environment beforehand, we'll need a way to quickly get them up to speed to any dangerous states using natural language in order to establish shared situational awareness and allow the human to safely assume control. So in the coming weeks, we're preparing to run an experiment involving a simulated maritime traffic control task set in a busy port to determine the properties of effective handover explanations. And then we also plan on validating an algorithm we've proposed, which we describe in a workshop paper from HRI 2020, which utilizes Monte Carlo simulation to determine failure modes and integer programming to generate human intelligible labels for those failure modes as they're clustered. And all of this would be for use in handover in a self-driving car simulator domain. And lastly, I'll discuss my Avalanche Rescue project with Akib Tabrez, Rick Gentry, and Aditi Periyanan, which is still in its formulation phases. So the idea here is to use groups of aerial drones to assist with human search and rescue teams in searching for both visual signs of avalanche victims as well as pings from avalanche transponder beacons. So we hypothesize that by maintaining a shared notion of uncertainty throughout the environment, by using a probability density map, which is a formalism already used in search and rescue contexts, we can keep the human in the loop as to where good and bad areas to search would be, and that they'd be able to locate a victim faster on average than if the drones simply stayed quiet until they found a victim. So in addition to the information itself, we're exploring the question of when to send the updates in order to avoid the human becoming overburdened by using an information theoretic update trigger we've developed, as well as addressing the question of how the information should be presented to elicit the ideal human action. So we're planning on using AR headsets to run a human subject study involving a simulated search task in order to compare all these modalities that we develop. So to summarize, here are some of the research directions I'm pursuing under the umbrella of synchronizing mental models for human-robot teams. So firstly, I'm interested in extending ArcLFD by using it as a vehicle to inspect, validate, and shape autonomously generated constraints in a form of interactive learning. I'd also like to validate our control handover explanation generation algorithms, which deal with autonomously conveying notions of playing risk. I'd like to determine the best ways to synchronize shared notions of uncertainty in human-robot teams through our Avalanche project, specifically with regard to the timing and the content of those updates. And lastly, I'm interested in leveraging new technologies like augmented reality, as well as the visual and language-based counterfactual techniques I described in order to improve human-robot performance. So I'll wrap it up there. Thank you everyone for attending today, and I'll open the floor for any questions.